Right, so to add on to what we did in class the last time, I have these two particular items here. First of all, synthetic division, which would fall in line, directly in line, and is a subset of the last topic we were dealing with in class the other day, right? The other thing is sort of separate, and that is identity of polynomials. I have a couple of examples set out there, and I will go through that coming out at the end of this video as well, right? Now, so let's deal with synthetic division. Okay. Now, synthetic division, first of all, is a replacement for long division, and also, of course, I showed you all the method of inspection the other day as well. Is a replacement for those two particular things, right? Now, the only time you would ever really need to use division of polynomials is when you are in the process of factorizing a cubic. You could do you could do long division, or you could do the method of inspection to do that, right? So synthetic division only really replaces that aspect of a factorization problem, right? The process of factorization and so on, all of the steps remain the same. This is just a very quick replacement for long division. Okay, so I have two examples set out here. I may add a third one just in case, because what I have here is cubic polynomials divided by linear. The syllabus says that you could get a polynomial up to order 4, right? So probably for a third example, I will add on a polynomial, a quartic polynomial, something containing x to the power 4. I will add that in, and I will show you all the synthetic division of it, right? So synthetic division, first of all, it corresponds directly to long division, right? A lot of the numbers that and steps that are in long division, synthetic division replicates those steps, but it leaves out a lot of unnecessary things, right? Now, one unnecessary thing that takes place in long division, if I were to jump back to a couple of long divisions that we did, right, let's take a glance at this one here. This was a situation where we did long division, right? As a matter of fact, I wouldn't look back at that example. Let me just do a long division based on what we have here, right? So the first one here, I have x minus 3, and I'm going to divide that into x cubed plus 2x squared minus 4x plus 5, right? Now remember, I spoke about the alignment of this polynomial here, in that this place is essentially place value columns, right? This is a column containing anything with x cubed. This is a column containing anything with x squared. This is a column containing anything with x. And this is a column containing constants, right? Now, those place value, or that place value layout there is understood, right? Similar to for example, numbers, right? Like, I mean, the mere fact I give you a number like this, let's say I give you the number 1983, right? That there is understood to mean 1 times 10 to the power of 3 plus 9 times 10 to the power of 2 plus 8 times 10 to the power of 1 plus 3 by 10 to the power of 0, or just 3, right? So this is the so-called expanded notation, right? Now, when you leave out all of these unnecessary things here, and you just write those digits alone there, it is understood what is meant, right? Now, so that there, having the x cubed itself, x squared, x, and so on, is a little bit unnecessary to some extent when you write a polynomial in this place here, right? With the understanding that the polynomial you are writing is a cubic polynomial, right? But that's not really what is the unnecessary part, right? So we have the division step, which is x into x cubed, which just gives x squared, and then you have to repeat that now with multiplication, right? So you just said x into x cubed, and you are following that up immediately by saying x squared by x, giving you what obviously has to be x cubed, right? So, and then you have to consider what happens when you subtract those two things, right? So this here is not necessary. That is understood, right? Now, it is understood to the extent that the answer you get on top here is already also known, right? Let me jump forward and look at a partial long division for number 2. This is divided by x plus 2, right? Now, that other polynomial, there is 2x cubed minus x squared and so on, right? So I will start off by saying x into 2x squared, which is going to give me what? Sorry, x into 2x cubed, which is 2x squared, right? Good. Now, a portion of that is kind of obvious because the coefficient here always repeats itself. If I have, let's say I have x plus 1 into 3x cubed. X into 3x cubed is 3x squared. So the same coefficient here comes back there. That is another unnecessary thing you write down when you do long division. The only time the coefficient will change is if it is not just x alone in the divisor position, right? So for example, if I do 2x plus 1 and I'm doing the long division of that into 2x squared, then of course 2x into 2x squared will be x, and now, well, of course 1x, right? But let's say 2x cubed, right? I'll get 1x squared. So only in the situation where it's not just x alone in this position here I have 2x, does this coefficient here change, right? Now I will get back to that aspect of it afterwards, right? But what is eliminated in synthetic division is that multiplication step where you are multiplying something or terms that you just divided, and then you still have to go back afterwards and perform a subtraction, right? Now, I have been leaving out the subtraction when I demonstrated this long division to you all, right? So as I was saying, x into x cubed is x squared. You have to repeat x squared by x gives you x cubed, and of course x squared by -3 as well, right? Good. Now, I already have alignment here. So this is the situation where this x squared becomes unnecessary because I have an, place value system. I don't need to write really and truly the x squared itself there, right? So then I do subtraction. So x cubed take away x cubed disappears. 2 take away -3. So 2x squared take away -3x squared. I don't even have to focus on the x squared. Those two terms are like algebraic terms. Both of them are terms in x squared, so I'm really just focusing on their coefficient. So the x squared is not necessary, right? 2 take away -3 is 5, of course, x squared. Now I have to bring down the minus 4x. Good. Bringing down itself is another redundant process because the -4x is already there, so you are basically copying it over there, right? So repeat again, x into 5x squared is 5x. So you see, whatever you get down here, that same coefficient appears up on the top there, right? Well, that is, of course, when it's just x alone, right? If it is not just x alone, well, obviously it will change, right? So as I was saying, 5x squared, x into 5x squared is 5x, so I have to do 5x by x, which is obviously going to give me 5x squared again. But more importantly, 5x by -3 is -15x, right? And again, I have alignment here. Everything here just contains x, right? So, as I was saying, subtraction will follow now. 5x squared take away 5x squared disappears. -4 take away -15. -4x take away -15x. So I'm just looking at the coefficient. -4 take away -15 will be 14. That actually, sorry, will be 11. X, and then you have to bring down the 5. So you are copying something that you had already written down before, right? And so on. You continue, right? X into 11x again. X into 11x is just 11, the same coefficient. And then x by that stuff there will be 11x minus 33, and then you subtract it and you will get 38, right? I hope my computation was correct. Yeah, okay, everything seems fine. So I know that my quotient is x squared plus 5x plus 11, and my remainder is 38, right? Now let me show you all what synthetic division, how synthetic division shortens that process, right? There is a single drawback with synthetic division. First of all, the divisor, so let me put synthetic division again here. Good. This is now a situation where the divisor must be of the form x minus a, right? So well, at least the limited technique that I'm showing you all, you can't do things, well, sorry, let me not talk about what is not yet. For example, you could do x minus 2, x minus 3, you could even do x plus 4, x plus 7, whatever it is, right? Once it is just x alone, right? But you cannot use it for something like 2x plus 1. So that 2x there, that's a problem, right? So you can't use this version of synthetic division if your divisor has a coefficient of x other than the understood 1, right? So you can't do 3x plus 4, anything like that. The 3x is a problem, right? So that is the only limitation, or the limitation of this version of synthetic division. You could only use it for divisors of the form x take away a. It doesn't have to literally be take away. For example, I could do plus 4, I could do plus 7. In the second question, I have x plus 2, and so on, right? So that's the first thing you have to make sure. Now remember, this is not non-mandatory to use this. I'm just showing you all this as an option, right? So your divisor has to be of the form x minus a, right? And what I'm going to do is I'm going to do the same question, obviously, using synthetic division, right? So your divisor must be of that form. That's one part of it. And then now you have to write it down in a very specific way. So what you are doing is you are converting, first of all, convert the dividend, the thing you are dividing, to a string of integers. The string of integers, right? So x cubed plus 2x squared minus 4x plus 5, you change that to just coefficients alone, right? Now you can't put them too close together. You have to sort of space them out a little bit, because unlike a regular number, like I had 1983 just now, I have negatives inside there. So I will put it as 1x cubed, 2x squared, negative 4x, and then 5. So I've converted that polynomial there into just a string of integers. Because I have 4 of them, it has to mean a cubic polynomial, because a cubic polynomial has 4 coefficients: coefficient of x cubed, coefficient of x squared, coefficient of x, and a constant, right? So if for some reason, you know, like let's say somebody tells you about a polynomial 2, 3, 5, 7, 9, right? That has 5 coefficients, right? Somebody, it wouldn't make sense. I mean, somebody would be committing a grave error if they think that this is cubic, right? Because if you start from the right hand side, this is a constant. This will be a term in x. This will be a term in x squared. This will be a term in x cubed, and this will be a term in x to the power 4. So it's not possible to confuse it, even when you are leaving out important things like x to the power 4, x cubed, and so on and so on, right? So this is undeniable. This, you know, the translation of this string back into polynomial, right? It is unambiguous, right? Now, I'm not saying that outside of doing synthetic division, you don't convert polynomials to just integer strings, right? But in this topic here, you could convert a polynomial to an integer string, leaving out all of the unnecessary stuff. And it is unambiguous that this means 1x cubed, 2x squared, negative 4x, and then 5, right? So you do that there, right? So let me show you all how to actually perform the synthetic division itself, right? So what I'm going to do is I'm going to take my polynomial string and I'm going to write it down, kind of similar to how I lay out or start off with the long division there, right? So I put my string down 1, 2, -4, and 5. And what I do is I take out the a from the x minus a, right? So I take out the a, and in this case here I'm dividing by x minus 3, right? So I'm taking this here and I'm dividing by x minus 3. So I take out the a. The a is 3. So I take the 3 and I put it there. Good. So I have everything kind of lined up there. And all of the working I'm going to do will be contained within this very small area here. All of it will be contained within this area here. So the first step, right? Well, actually, I have a little extra down here I'm going to do, right? The first step is to take the first digit and carry it down, right? So that 1 there, I carry it down there, right? Now, that is the equivalent, that 1 there corresponds, if I go back to the long division on the previous page, that corresponds to this 1 here, right? Now, a big part of synthetic division is recycling coefficients once you obtain them. So, for example, this 5 is the same 5 up there. This 11 is the same 11 there. So, instead of trying to do division, once you get a certain number, you could just recycle it and it becomes a part of the answer, right? So, that is just similar for me, to me here having 1x cubed, and that 1x cubed is going to give me just 1x squared. 5x squared is just going to give me 5x. 11x is just going to be 11, right? So one of the steps in synthetic division is just simply bringing down a number once you get it, right? But we'll deal with that just now, right? So yeah, right. So in other words, the division, although we are doing division, the division step is actually not necessary, because whenever we do division, we are just dividing by x alone. So you take 1x cubed divided by x, you will get 1x squared. You take 5x squared divided by x, you will get 5x. So the division is actually not necessary. What is important is the multiplication here, for example, x squared by -3, and then the subtraction. Those are really the important things, right? So although we are doing division, the important step is the multiplication and then the subtraction step. So in synthetic division, you only do multiplication and subtraction, right? Now, the process is altered a little bit in that you aren't really actually going to do subtraction, you're going to do addition. And the reason is this, right? What I've done is I've taken out, I am dividing by x minus a. But I have not taken out -3, I've taken out +3. So what that converts everything to, instead of addition, instead of subtraction, I'm going to do addition, because outside here I have +3, whereas when I do long division, I had -3 on the outside here. So that is one difference in the process itself. Now, good. Anyway, as I was saying, so I'm going to do 3 multiplied by 1 is 3. Right? You know what I'm going to do? Actually, I'm going to alter things a little bit, right? Because I wanted to, I know that you all are accustomed doing long division, so I don't want to have the process too different to long division, right? So I'm going to change what I just told you all there. When I have x minus 3 instead, you take out, I'm going to take the -3 outside there, so that when I go inside there, I'm going to do subtraction. So it will even more closely resemble long division, the long division process that you all are accustomed to, right? So I'm changing it a little bit here. So -3 multiplied by 1 is -3. So I do the multiplication and I put the -3 there, right? So what I'm going to do now is subtraction. So I just did the multiplication step and I'm going to do subtraction, right? So subtraction. 2 take away -3 is 5, right? Now that is this 5 that I have on the left hand side there, right? It's the same 5. I had -3, and I did a computation there, 2 take away -3, and I'm also doing 2 take away -3 here. Now, once I got 5, again, the division step didn't really change anything. 5 is a part of the answer, so I have my answers down here already, right? Good. So I did my multiplication, I did my subtraction. There's no division when you do synthetic division itself. It is only multiplication and subtraction, right? So I'm going to repeat now. So -3 multiplied by 5 is -15. And we do indeed have -15 on the left-hand side there. This is the same -15 here. So what am I going to do now? Subtraction. -4 take away -15 is 11, right? Again, I got 11x. 11 is a part of the answer, right? Now let me go again. -3 by 11 is -33. Subtraction, 5 take away -33 is 38, right? So these same numbers are there in the long division process, and this is much less writing, much more quick, because there is nothing to consider with doing actual division or multiply. Or I'm sorry, there's no actual division taking place here, and that is why it is called synthetic division. You don't actually do division. It's really multiplication and subtraction, right? Right, now comes the last part of it here, which is interpreting what those numbers below there mean, right? Now, when I'm setting up my structure here in which to do synthetic division, right? Because I have one number on the outside here, a single digit on the outside here, right? What I do is I usually block off the final space there and treat it as something special, right? And I mean, we already know what the 38 means. The 38 means that is a remainder. So what I have here is these 3 digits here are my quotient. So the quotient is not, well, I don't know how you will say that, but 1511, obviously. These are coefficients that could be translated into a polynomial, right? I'll put it down afterwards. So this is the quotient, and there's a remainder there, right? So my quotient, following this synthetic division, is what? Now, it has 3 numbers there, 3 integers there, right? Those 3 integers are the coefficients of a polynomial. The polynomial has 3 coefficients, so it has to be a quadratic polynomial. It cannot be cubic, because if it were cubic, it would have four of them, right? This one has 3, so it has to be quadratic. So this is 1x squared plus 5x plus 11, right? And then this here is the remainder. And we already know that the remainder is 38. Okay, so this here is a replacement for long division. It is done very, very quickly once you get accustomed to it. So, and I mean, it is a departure from the norm. The norm is to do long division, right? You are not, doing some drastic shortcut that is not valid. It is perfectly valid, because clearly it is the same numbers that you get there. So once you identify that there's a lot of unnecessary and redundant and repetitive steps and so on in long division, now you could clearly see, right, that this method here, there's absolutely nothing wrong with it, right? So let me very quickly demonstrate number 2. And then we will see, right? So my divisor again is x plus 2, right? My divisor is x plus 2, right? Now, how I would normally do it, instead of putting x plus 2, I would treat it as x plus -2. So I would, in my usual way of doing it, is to put -2 outside, but I'm not showing you all that one, right? But either which way you do it is going to be valid, but you have to know, what changes when you decide to change the sign of the number, right? So I take the 2 and I put it outside there like that, and I have my little box structure thing. This 2x cubed minus x squared minus 7x plus 6, I have to change that into a string of integers. Right, so let me do that there one time. Let me put it up here. So this is 2x cubed minus 1x squared minus 7x and then 6, right? So I stop there and I continue drawing my blocks like this here, right? So there are basically 4 place values in this particular structure here, right? So now I'm going to have 4 numbers down here, right? So what I do is I box, so I have 1 digit outside here. So I'm going to box off the last space there, and whatever goes into that space is going to be the remainder. Okay. So what do I do? First things first is to bring down this number here. I bring down the 2, right? Because we are dividing by x plus 2, I would have said x into 2x cubed is 2x squared. That doesn't change the coefficient, right? Again, once it is of the form x minus a, the division step does not change the number in this process here, right? So I bring down the 2 to start off. Now I do multiplication. 2 by 2 is 4. And I put the 4 there. What do I do now? Subtraction. So it's really just multiplication and subtraction. So -1 take away 4 is -5, right? Multiplication step is to follow again. 2 by -5 is -10, and I do subtraction. -7 take away -10 is 3. 2 by 3 is 6. 6 take away 6 is 0. So my quotient here now, and I have 3 numbers there, 3 coefficients, so it has to be quadratic. So my quotient is 2x squared minus 5x plus 3, and my remainder is, well, 0, right? So I mean, if I were doing factorization, this would be my quadratic thing. So you know, if I'm in the middle of a factorization question, I would then go on to say that f of x, you know, is equal to what did I divide by? X plus 2 into 2x squared minus 5x plus 3, and then I just go on to factorize that thing there. So this is x plus 2 by 2x minus 1 by x, sorry, yeah, by 2x, yeah, minus 1, then x minus 3. Yeah, will that work? That probably wouldn't work. So let me say 2x minus 3 by x minus 1. I'm pretty sure that is going to work now. Minus 3x minus 2x is minus 5x, right? So, right, so you see it takes care of the long division thing. It gets it done very, very quickly, right? But again, the limitation is the fact that you could only do synthetic division if your divisor is of the form x minus a. Right, so I did say I would add on a quartic polynomial, but of course linear divisor still, right? So I have 3x to the power of 4 minus x cubed plus x minus 1. I want to do synthetic division, right? So first thing I have to do, my dividend has to be converted to a string of integers, right? And those integers now are going to represent the respective coefficients, right? So it is 3x to the power of 4, right? Minus 1x cubed. Now you notice there's no x squared term, right? So, but I have to compensate for that, because if I leave it out and I just put 1x minus 1, somebody will look at this and see 4 coefficients and think that it's cubic, right? So again, you have to put in, because it is quartic, it has to have 5 coefficients. A coefficient of x to the power 4, coefficient of x to the power 3, a coefficient of x squared, a coefficient of x, and then a constant. So you must have 5, right? If you leave out the coefficient of x squared, even though if in this case here it is not given, then you would be misrepresenting what the polynomial is when you convert it to the integer string, right? So coefficient of x to the power 4, coefficient of x cubed, you have to put in a coefficient of x squared, so you need to put 0, right? And then of course coefficient of x, and then the constant, right? Coefficient of x is 1 and the constant is negative, right? So that is the proper way to do it, right? I mean, if you ever find yourself in a situation, they did have up to fourth order polynomials. They do have it in the syllabus, but I've never really seen it, you know, to tell you the truth, in the past papers also, right? So I'm divided by x minus 2, so I'm going to put -2 outside there. And I do up my little, you know, my little grid or whatever you want to call it. So this has 5 place values here, right? So of course, because I have 1 digit outside there, what I'm going to do is I'm just going to reserve this last place value here. Okay, treat that as something separate, because that is going to be the remainder, right? So what is the first step in the process? The initial coefficient, you bring it down like that there, because if you were doing long division, you would say x into 3x to the power of 4 is 3x cubed, right? So, right, so you bring down that first coefficient there. Then you are following it up recursively with multiplication, subtraction, multiplication, subtraction, multiplication, subtraction, right? So -2 by 3 is -6. Let's do subtraction. -1 take away -6 is 5, right? So multiplication, subtraction. Multiplication again is up now. -2 by 5, right, is -10. Subtraction, 0 take away -10 is 10. Good. Now, -2 by 10 is -20, right? Subtraction, 1 take away -20 is 21. Good. -2 by 21 is -42. Subtraction, -1 take away -42 will be 41. That 41 is my remainder. Okay. Look, you got to be very careful about this string of digits here. How many digits? 4. Sorry, not how many digits. The string of numbers here. The string of integers here, right? How many of them are there? 4. 4 integers, right? You have to translate that or retranslate it back into a polynomial. What kind of polynomial has 4 coefficients? Cubic polynomial. So it has to be that the quotient is 3x cubed, right, plus 5x squared plus 10x plus 21, and the remainder is what? The remainder is 41, right? So that is how you do synthetic division. You could well imagine how long this would have been if I were doing long division, right? No, I took long because I was explaining it while I was doing it, but in all practicality, you get accustomed to this. This is literally 20 seconds and you are done, right? Good. So of course it is it doesn't it only replaces, in the topic we were doing, it only replaces the long division thing. Or if you were doing the method of inspection, right, it replaces that particular process, right? But if you were doing a factorization question, you would still have to, you know, get the quadratic factor that complements the linear factor you would have found, and then go and factorize that, and so on, right? So it doesn't change that aspect of the topic, but it replaces long division, right? So that's all I have to say concerning synthetic division. I'm going to put on a couple questions on a worksheet for you all to do, in addition to basic remainder and factor theorem questions. The next thing I want to discuss, which is identity of polynomials. I will begin on that one time and include it in this video as well, right? So let me just go back up to, oops, I'm going in the wrong direction. So this is right, so this is identity of polynomials here. Switching gears to this now, right? So they want you to here now, this is like is not really a part of this topic, you know, but it is, you know, occasionally they bring questions like this in place of you know, proper remainder and factor theorem questions. So this is not really remainder and factor theorem, right? But it is, you know, it is there. Okay, it is in the syllabus as a separate thing under the topic algebraic operations, right? The questions, they really and truly, they don't come very often, right? Now what I have here, you would notice now, I just want to change this c to lowercase c, right? So what I have here is I have a polynomial. Well, first of all, is an identity, right? You see that symbol there? Identity, right? Now, an identity is something, you all would have met some limited identities, especially trigonometric ones, etc., when you all were in Form 5, right? Now, when you are doing an identity or working with an identity, you don't take something from one side and put it on the other side, right? You don't do that, right? What is on the left is identical to what is on the right. You don't ever shift something from one side to the other. You could do that with an equation, but you cannot do that with an identity, right? So the identity now, the left-hand side is the left-hand side, separate and distinct from the right-hand side, which is the right-hand side, okay? So what I'm going to do, if I want to work out these unknowns here, is I'm going to, if I have brackets, and I do have brackets actually in the first question on both sides. So what I'm going to do is I need to try to find out the value of A, and I need to try to find out the value of B, and I also need to try to find out the value of C. So I have unknowns there, right? So what I'm going to do is I'm going to work on both sides of the equation, of the identity, sorry. I'm going to expand and simplify the left-hand side. And I could do it in the same line. I could expand and simplify the right-hand side. So I don't ever take something from one side and put it on the other, right? If you are doing that, don't. Cease and desist, right? Mathematically speaking, an identity is not to be interfered with in that manner, okay? So anyway, as I was saying, so if I want to work out number one here to get the value of the unknowns A, B, and C, what I need to do is I need to get this kind of partially weird factorized looking thing here into a pure polynomial, in that, you know, the distinct terms are just a coefficient and a power of x, a coefficient and a power of x. So I want to expand out that, and I'm going to expand out this one as well, right? When I come to number two, I'll be doing the same thing. You could see that the expansion here is going to be a little bit, you know, interesting, right? So number one, so I have, let me just copy it over. A, open bracket, x minus 1 by x plus 1. That shouldn't be too bad to expand, and then bx, right? Is identical to, sorry, 4x squared plus, no, I need to perform the expansion of c plus x by x minus 1. I'll do that after I do the left-hand side. So then this means that, well, I mean, x minus 1 by x plus 1 is easy enough. So this is a by x squared minus 1 plus bx. That's the left-hand side. Let me do the right-hand side now. So 4x squared, and I'm going to do this expansion here. C by x is cx. C by negative 1 is negative c. X by x is x squared. And then x by negative 1 is negative x, right? So I've expanded, well, not fully as yet, but I've expanded in that line there. So let me just continue with simplifying. On the right hand side, everything is fully expanded, so I could just regroup, you know, everything together, pull the common terms together, and so on, right? So what I want to have is I want to have distinct, I want to group the terms together, and I don't want to have multiple x squared terms and multiple x terms, right? You know, I simplify as far as possible. So I want to have one x squared term, right? So of course 4x squared plus, well, 1x squared, well, that's just 5x squared. That's easy. That's not really what I'm talking about. What I'm talking about is this here, cx minus x, right? I'm not going to leave that as two separate terms. So what I'm going to do there is I'm going to put a plus, and I will extract the x out of those two terms, and basically like a factorization of just those two terms, right? So this will be c take away 1, right? And then I have, just gonna make that separate. What do I remain with that I haven't dealt with yet? Minus c. That's just a constant. So I just kind of put that one side there. So I've converted it to a polynomial, that nice pure looking polynomial like that. Term in x squared, a term in x, and then a constant, right? So quadratic, of course. The left-hand side is quadratic as well, right? You can't have, you know, you could only have identity if the order of the polynomial is the same as well, right? So let me do a little expanding and so on the left-hand side now. A x squared minus a and bx, right? So I'm just going to regroup it for it to look nice, right? I think it is fairly obvious, so I could delete this here and just put it in that form one time. So ax squared plus bx, and then I have the minus a over there, right? So I have a polynomial on the left and a polynomial on the right, and both polynomials are written in what is called descending powers of x. So I start with the larger powers of x, and then I decrease my power of x termly going down, right? Right, so now I can make a comparison, right? So I'm going to compare the terms on the left-hand side with the terms on the right-hand side, right? Now this is mixed up with the method of inspection that I was showing you all before, right? So now I could basically look at the left-hand side and right-hand side, and I could tell the value of certain things immediately. So for example, if I look at the terms in x squared, I realize that I have ax squared there and I have 5x squared there. The only way these two things could be identical is if the coefficient of x squared on the left side and the coefficient of x squared on the right side is this exact same thing. That is what identity is about. So it's not that I'm going to take everything on the left and put it equal to 0 and try to get a quadratic equation. No, I leave what is on the left and I leave what is on the right. And I just compare them when I get to this polynomial stage here. So clearly, a is equal to 5, right? If you want to be, you know, in the good old days, we used to say a equal 5, you know, by inspection, we used to say, you know, like, that's basically like, you know, telling the examiner, well, if you look at it, you could clearly tell that a equal 5, right? But, you know, we don't communicate in that kind of language again. You know, you try to be a little bit more, I don't know, formal, you know, not be too presumptive or whatever it is. So we'll just say the terms in x is going to give us the fact that a is equal to 5. Sorry, not the terms in x, the terms in x squared, right? Good. What else can I get the value of immediately? I don't have to literally go through it term by term, you know. I could just kind of look at this and realize, well, I know the value of a. So I know this is a constant. And then this is a constant here. So this is a constant. And that's a constant. Now I know the value now of the constant on the left-hand side. The constant on the left-hand side is basically -5. So let me look at the constants now. What are the constants? Negative a has to be equal to -5. Sorry, negative c. So what does that mean? It means that c is equal to a. So that means c is equal to 5. So I have my other value there, right? So let me go now to the terms in x, that's this here, bx and c minus 1x, right? So the terms in x on the left side and on the right side have to be the same as well. So bx has to be the same thing as c minus 1 times x. So this means that b is equal to 5 take away 1, which is 4, right? So this here is, it is essentially the method of inspection, except that you have to do your expansion fully on both sides, right? So that is how I determine those unknown coefficients, right? Now note, I do not pull everything on one side, get 0 on that side. It is not it is a quadratic, yes, on both sides, but it's not a quadratic equation. It is an identity of quadratic polynomials, right? So there's no carrying something over there. There's no multiplying throughout by something. You don't do that with identities. You do that with equations. These are not equations, these are identities, right? Let me look at number 2. Number 2 is kind of more in line with one or two of the questions that Cape would have presented. So number 2, well, the right-hand side luckily is already expanded for us, right? So really and truly the work is on the left-hand side. So what I'm going to do is I'm just going to pull out the left-hand side here and work with that, and then, you know, then put it back into the identity. So I'm just working with the left-hand side strictly now. So ax plus 1 by x plus b by x minus 1, right? I need to expand it. I mean, clearly the right side is cubic, so the left-hand side is going to be cubic as well. So I need to get that into some kind of cubic looking form, right? So let me expand. I'm going to take a pair of brackets, multiply all that, and then take the result of that and multiply it by x minus 1, right? So let's do that, right? Ax by x is ax squared. Ax by b is abx, right? 1 by x is, well, just 1x, and then 1 by b is, right? Now I'm not going to do the, you know, pulling everything together, and and so on as yet, because I'm still in the process of expanding, right? I have x minus 1 here. So this is ax squared by x, right? Those arrows are really long. I'm not going to draw them, right? I think you all understand what's taking place here. I have to take each term here, multiplied by x, then do the same thing, each term by negative 1, right? So ax cubed plus abx squared plus x squared again. X by x is x squared, right? Plus bx. So that is each of these terms here multiplied by x. Now I have to do each of those terms multiplied by negative 1. So it'll be minus ax squared minus abx minus x minus b. So now I'm going to try to group those common polynomial coefficients together, right? And then powers of x, right? Well, there's only one x cubed term, that's ax cubed. What do I have with x squared? I have abx squared, I have x squared itself, and I have minus ax squared. Those are 3x squared terms. So let me pull all the coefficients together in a bracket. ab plus 1 minus a, all of those are my x squared coefficients. Do I have multiple x terms? I do. I have bx here, and I have abx, and I also have minus x, right? I dealt with this one already. That is just that, right? So far I've kind of dealing with everything, and then this minus b is going to remain after. I'll come to that. Let me talk about the terms in x now. bx minus abx minus x. So the coefficients now b minus ab minus 1, all of those are terms in x. And the only thing I have remaining afterwards is that just that minus b there. So minus b. So I have it in a polynomial form. So this would mean then that left hand side, right hand side, right? So ax cubed plus I'm really not feeling to write that over again. So what I'm going to do is I'm going to put right hand side, put on the right hand side below it, 2x cubed plus 5x squared plus cx minus 3, right? So clearly, the terms in x cubed, let me switch up my color a little bit here. So I'm going to look at the terms in x cubed now, because that gives me the value of a off the bat, right? These are my terms in x cubed, so what a is equal to 2. I have that there, right? Now what I'm going to do is I'm just going to look down and compare it. So I'm just looking through the problem to see. So this has to be 5, this here has to be c, and then this here has to be negative 3. So you see, when I go to this term here now, I realize I could get the value of b there, just from the last term itself. So I'm not just robotically just going through what I start with this coefficient. Let me go to this coefficient now and then see what happens, and then go to this. I look at what is in front of me, and I decide what is the next best step. The next best step is for me to go to this b here. So clearly negative b is negative 3. So b has to be 3. So I can get the value of b from it, right? So I'm going to look at the constants. Now, constant on the left hand side is negative b. The constant on the right hand side is negative 3. So this means that b has to be equal to 3. So I have a and I have b. Now I could go to probably my x squared term. So let me look at the terms in x squared on both sides, right? What is the term in x squared on the left hand side? Well, the coefficient of it is ab plus 1 minus a, and the term in x squared on the right hand side is, well, that's just 5, right? That doesn't really help me with anything, to tell you the truth, right? But what I could do is this here, this is basically like a check, right? So what I'm going to do is I'm going to just make sure, or see if that really does indeed give me 5, right? So what is a? A is 2, b is 3, plus 1 minus 2, is that equal to 5? 6 plus 1 is 7, 7 take away 2 is 5. So that means my value of A and B are good, right? That isn't necessary. So let me go to the terms in X now, right? So because the coefficient of X is C, right? So B minus AB minus 1 is equal to C. So now I know that my A and B are good, so I could safely use them here to get C. So 3 take away 2 by 3, take away 1 is equal to C. So this is 3 take away 6, take away 1, right? So this is negative 4. So therefore my final answer here is that A is equal to 2, B is equal to 3, and C is equal to negative 4, right? So that is how you handle those identical identical polynomials, and the method for finding those unknown constants or unknown values inside the identity itself.